morning. So today's class, I'm going to discuss Module 5, Free Vibration. Vibration of a system may be started by the application of some external force, or some disturbance, some initial disturbance in a system can produce vibration. And this vibration, which is produced due to some external disturbance, and that external disturbance is withdrawn, or that external force is subsequently withdrawn. That vibration, the resulting vibration with no external force acting on it, is termed as free vibration. Example, vibrations of a tuning fork. You just give a hit on the tuning fork and that force is removed, that hammer is removed from it. So it goes on vibrating. Similarly, the vibrations of a guitar string. Vibrations of structures induced by earthquake. Earthquake induces vibration, and during the time of vibration, the force need not be there on the structure. So such cases comes under the category of free vibration. So free vibration is the vibration. For inducing the vibration, there should be some external source, but that external force or source is not acting on the structure during the course of vibration. So that is the first definition. Second one, forced vibration. If the external force is acting in the system during its vibration, it is termed as forced vibration. Examples, vibrations due to reciprocating and rotating masses in IC engine. So inside the automobiles, or we have a reciprocating engine mechanism. The piston will be connected to the crank and there will be some vibration induced, but during the course of vibration, that reciprocating mechanisms, masses are acting inside the structure. Machine foundations. See, in the foundations where the machines are installed, as the machine rotates, the foundation will be subjected to vibration, and during the entire course of vibration of the foundation, the machine will be operating above the foundation itself. So, vibrations of machine foundations. And the next one is wave forces acting on offshore platforms. So the offshore platforms which are installed in the ocean, in the sea, as the waves hit on it, the platforms go on vibrating. So the source of vibration is the wave force. It continuously acts on the system. So these are the two type of classifications. The vibration can be either free vibration or forced vibration. Another one important term here in this portion is degree of freedom. Degree of freedom of a physical system is defined as minimum number of independent coordinates required to define completely the position of the mass at any instant of time. So if we want to define the position of a vibrating system, position of the mass, suppose at t is equal to 0, it is at one location. After t seconds, if you want to specify the position of the system, if we just require only one coordinate, then it is called single degree of freedom system. So depending upon the degree of freedom, the vibratory system is divided into three classes: a single degree of freedom system, multi-degree of freedom system, and continuous system. Let us see one by one. A single degree of freedom system, if a single coordinate is sufficient to define the configuration of the system at any time, it is known as single degree of freedom system. Let us see. I'm shown here, say, a water tank structure. This is a water tank resting over the supporting structure. The supporting structure consists of columns and braces, etc. It's fixed on the ground. It is continuously subjected to wind forces. So the actual structure is a water tank structure subjected to lateral forces or horizontal forces. In order to analyze this particular structure, we make it as a simplified model. We assume that the entire mass of the structure or the water tank is concentrated here. That is called the lumped mass. So this is the lumped mass, M. The entire mass is assumed to be constant at the surface. And how much it will deflect on subjected to this load. This load is denoted by P, and the load varies with time, Pt. Always the load is dependent on time. As time progresses, the load varies. So the entire load system is marked by Pt, and the stiffness of this column, stiffness is load required to produce 1 millimeter deflection. If how much stiff these columns and bracings, depending upon that, this body will deflect. So the stiffness of this entire supporting system is represented by this particular line, and subject to a load, this is bottom and this fixed. So there's a chance that it will buckle like this or it will bend like this. This is the bending shape of this. So after a certain time, the mass will come here. So the distance, this distance x, if this x is known, I can define the position of the structure after a certain interval of time. So with one coordinate, with this one coordinate x, with this one coordinate x, I can specify the position of the mass after a certain interval of time. Hence, this is called a single degree of freedom system. So just one coordinate, this x coordinate alone is required to fix the position of the system. So if you model it, we can represent, when you do dynamic analysis, we model it as a simple spring mass model. So this entire mass, this is now constrained. We are considering only the horizontal displacement of this mass. Actually, in the space, it will be having displacement in x direction, y direction, and z direction. But I am considering only the horizontal displacement of the mass. So it is single degree coordinate system or single degree freedom system. So this mass is restrained to move only in horizontal direction. So I have marked the mass. So I show it. This mass is fixed on rollers. Rollers means this is possible to move only in x direction. So the mass is shown in rollers. So x displacement at any time. The center of the mass is having a displacement x. The displacement also varies with time. Hence it is shown xt. Now the entire stiffness of this column is shown by a spring. So okay, and it is fixed at the bottom. So it is fixed here. So and the force P. So this much represents. So this represents the spring mass model of the single degree of freedom system, or analysis of a structure, water tank structure subjected to lateral force can be brought to this mathematical model or called the spring mass model. Now I have to write the equations for this particular model and solve the equation and get x so that I can get what is the position of the mass. So here the K is representing the stiffness. Stiffness is the restoring force. Once the force comes, it deflects, but the structure always has a tendency to come back to its normal position. So K represents the stiffness. Stiffness is nothing but the load required to produce unit deformation. Newton per meter. Very, very important. Always in examples, you put Newton per meter. It is the restoring force. Spring represents. And M is the mass. It should be in kilogram. Okay. So, have got an idea what is a single degree of freedom system. Now coming to multiple degree of freedom system, if more than one independent coordinate is required to define the position of different points in the system, it is called multiple degree of freedom system. Let us consider a multi-storied building. Say a two-storied building I am taking for reference here. It is subjected to a horizontal force like this, some wind force. So the entire mass of this floor is represented by like M1. Lumped mass we call it. Entire mass of this second floor slab, that is represented by letter M2. So, and the stiffness of this column, depending upon the stiffness of these two columns, this mass will rotate, this mass will move. So the stiffness of this column, this much portion is K1, and the stiffness of this entire portion, depending upon the stiffness of this entire portion, this mass will move. So this is the simplified model. The actual structure is simplified as a lumped mass system like this, a vertical line representing the stiffness of the supporting structure. M1, M2 are the masses. Suppose if I want to get the position of this two masses after a certain interval of time, I should know how much, this is the deflected shape, how much the mass M1 moves, that is X1. How much the mass M2 has moved, that is X2. This will be different. Okay, so this system where two coordinates are required here. X1 and X2 should be specified if I should know the position of this entire structure after a certain interval of time. So let me represent as a spring mass model. Mass M1, it is permitted to move in X direction only. So a mass M1 is put on rollers. And how much it will deflect will depend upon the restoring force is dependent by the stiffness of this column. So the stiffness of the column is represented as K1. Now second mass M2, that is also put in rollers. Its displacement X2. And the stiffness of these two columns put together, that is X2, K2. Stiffness is K2. So the mass M1 on spring K1, mass M2 on this column, the stiffness of this much column is K2, and the displacement of X1, displacement X2 for the second mass, the load P. So this is the simplified model or the spring mass model for this two-storied building. So this is called a 2 degree of freedom system. So depending if it's a 10-storied building, we can idealize it as a 10 degree of freedom system. Now in certain cases, in order to have detailed analysis, for example, a beam like this, we call it as a cantilever. One end is fixed and the other end is free. If you want to, it's a cantilever like this. Suppose it is subjected to a dynamic load, a load which is varying with time. Say it deflects like this. If you want to do the analysis of this, we can assume that the mass, we can split up into small intervals, and the mass is concentrated at the center of each of these strips. The mass is assumed to be concentrated on the center of each of these strips, or it is assumed to be distributed over the entire length of this beam. So the mass of a system such as a beam is uniformly distributed over its length. The mass is considered to have, so each small masses will have each vertical degree of freedom. So this will be having this much displacement, the next mass will have another displacement. So we can assume it to have infinite degrees of freedom. That is, the infinite number of masses concentrated at different points has infinite degree of freedom. Such a system, we call it as a continuous system. For a continuous system, the degree of freedom is infinity. So degree of freedom is the number of coordinates. So if you want to fix the position of this mass after a certain interval of time, I should know this y1, y2, y3, y4, y5, etc., y infinity. So the number of coordinates required to locate the position of a system at a certain instant of time is called degree of freedom. And if only one coordinate is required, it is called single degree freedom system. If more number of coordinates are required, it is called multiple degree of freedom system. If infinite number of coordinates are required, or infinite degree of freedom system, it's called a continuous system. Infinite degree of freedom system is called a continuous system. Now next term which you have to be familiar with in this chapter is damping. All these you may get part A questions, 3 mark questions, or even 5 mark questions in part B. What is damping? We have seen when a structure is subjected to vibration, say suppose on an advertisement board you have seen in the roads, suppose due to a wind gust, it starts vibrating. But after a certain interval of time, the vibration reduces and it finally comes to stop. So that process, the resistance to vibration is called damping. The resistance to vibration is called damping. As a result of the energy dissipated due to damping, the amplitude of vibration reduces with time. You know what is amplitude? You have seen what is amplitude? The amplitude of vibration means this is, suppose a body is, if there is no damping, say if you represent the displacement of the structure along this axis and time along this axis, this is a periodic motion. So we can represent it like a periodic motion. If this is the amplitude, the displacement from the mean position, this is the mean position to the top extreme, then the body moves to the bottom extreme. So these are called the amplitude. The amplitude of vibration is maximum displacement from mean position. If it remains same throughout the motion, then there is no damping. But actually what we see in practice, so initially it will be having this much amplitude, on the next cycle it reduces, and finally it damps out. So this the damping in the system is responsible, or due to internal friction in the material, it may be due to internal friction or due to drag effects of the surrounding medium. For example, in a vibrating system, a body moving inside a liquid medium, a piston moving inside a fluid inside a cylinder. It's the drag effect of the fluid. The vibration reduces, the amplitude of vibration gets reduced. So the most common representation of damping mechanism is called a linear viscous dashpot model. So damping is the resistance to vibration, and as a result of this, the amplitude of motion reduces with time and it damps out. The vibration damps out, or it comes to stop. The displacement becomes zero finally. So the damping is usually represented by a dashpot. So in the system, suppose if we consider the damping also, initially we have seen a spring and a mass alone. Okay, now we will be introducing a dashpot. Dashpot means inside a cylinder, a piston is moving. Inside a cylinder, some liquid is there and a piston is moving inside the cylinder. This is called the dashpot mechanism. And in the viscous damping, there are different types of damping. We need not go into that details at this particular first year level. Viscous damping is, we assume the damping force is proportional to displaced velocity. The damping force, C, is called the damping coefficient. That is a material property. And the damping force is proportional to velocity of the system, or the damping force is C into X dash. X dash means dx by dt. Spring force, how will you calculate the spring force? F suffix x. Spring force, restoring forces, K into X, where that is proportional to the displacement. If the structure moves by X displacement, K is the spring constant or stiffness of the spring. K into X will be the spring force. So in this system, there is the two forces restrict the motion. The damping force, which is C into dx by dt, or Cx dash, and the spring force that also opposes the motion, that is K into X. Okay, so these are the restoring forces. Now I have shown what is a free vibration. If a free vibration, where is no damping, say this goes on vibrating with the same amplitude. The amplitude remains same for the entire motion. It continuously vibrates at the same amplitude. X plotted versus T. So this is a free vibration without any damping. Amplitude remains same throughout the motion. And if it's a damped vibration, that is, a vibration is having some damping effect, that is resistance is vibration, the amplitude on each cycle decreases. After each cycle, the amplitude decreases. So this is a variation of displacement with time. So in the last year university question, there was a 5 marks question, differentiate between a free vibration without damping and with damping. So if you illustrate what is damping, you give the definition of damping, and if you give these two figures, it will be clear that you know the concept of damping. Now what is the equation of motion for free vibration? That is our next thing. So it's a free vibration. Free vibration means the system is starting the vibration by inducing some external force, by applying some external force, but the force is not in the structure at the time of vibration. So the external force is equal to zero. So in the spring mass model, there will be only the spring K, the mass M, this is the mass M, and the displacement of the mass is shown by xt. There is no phi. The P is equal to zero. This is the spring mass model for a free vibration system. So let us come to the forces acting on this mass. I am coming to the forces acting on the mass. I have marked the mass M. The restoring force K into X is acting opposite to the direction of motion. This is moving in the rightward direction, right direction. X is shown this. So the opposing force is K into X, spring force, the only force. Now we have seen D'Alembert's principle in kinetics of rigid bodies. What is D'Alembert's principle? So this mass is subjected to only one force, K into X. P is equal to zero. So I have not marked it. So the external force, together with the external force, we apply the inertia force. Inertia force is mass into acceleration, opposite to the direction of motion. So I am applying M into A, opposite to the direction of motion. If X is the displacement, then acceleration will be d square X by dt square. So spring force is K into X. The inertia force is M into X double dash. X double dot means d square x by dt square. The inertia force is applied opposite the direction of motion. Now the system is brought to dynamic equilibrium. So we can apply the principle of statics. Let us write sigma h is equal to 0. Motion is in x direction. So sigma h is equal to 0. Kx or mx double dot mass into acceleration plus kx is equal to 0. This is the equation of motion of free vibration. Let us divide this entire expression by m. So x double dot plus k by m into x is equal to 0. Let us put this k by m. K is the stiffness, m is the mass. K by m is defined as omega square. So d square x by dt square plus omega square x is equal to 0. So omega is root of k by m. So we define the term omega equals root of k by m, which is called the angular frequency of vibration in radians per second. So d square x by dt square plus omega square x is equal to 0 is the equation of motion of simple harmonic motion. If you consider a simple harmonic motion example, the equation of motion for simple harmonic motion is d square x by dt square plus omega square x is equal to 0. The governing equation for free vibration of a system is also d square x by dt square plus omega square x is equal to 0. So the free vibration of a spring mass system, the free vibration of a system is nothing but simple harmonic motion. So the free vibration is simple harmonic motion. So any simple harmonic motion, we can represent it by a periodic motion. That is what we have shown earlier. So you just remember this term. Omega is equal to root of k by m. If you know this expression, we can solve all the numerical examples from this portion of free vibration. And very, very important is in the question, you will be given stiffness in different units other than Newton per meter. So always first step, convert stiffness to Newton per meter. That is very, very important. Then mass in kilogram. Only then we will get root of k by m. K is Newton per meter and mass in kilogram. We will get the answer of frequency in radians per second. Now the time period. Time period is time for one oscillation. That is starting from here, go to upper extreme, the lower extreme, then come back to this. This is the time. This much time is called the time period. We know for one full cycle, if omega is the angular velocity, omega into time, time for one cycle is t, that is equal to, one cycle means 2 pi radians. Omega into t is equal to 2 pi radians. So time period t is equal to 2 pi by omega. So t is equal to 2 pi omega. And if this is circular frequency in radians per second. If you are asked to find out the natural frequency in hertz, number of cycles, natural frequency is nothing but number of cycles in 1 second. So if you know the time period, 1 by t. 1 by t is the natural frequency in hertz, which is equal to omega by 2 pi. Now coming to certain cases, we may be having, we can represent the system by multiple springs. Say this case, this shows there are two springs, K1 and K2 are attached to a mass. And this mass is subjected to a vibration, it is subjected to a displacement x in this direction. So it goes on. We apply a force in this direction, the system goes on vibrating. So if you are to solve this type of examples, these two springs has to be modified with a single spring whose stiffness is called the equivalent spring stiffness. So the displacement of the mass will be the same in this case as well as in this case. So the spring K1, K2 are replaced with a single spring whose constant is K equivalent. And in this case, we can find it out as 1 by K equivalent is equal to 1 by K1 plus 1 by K2. What happens here is when it is subjected to a displacement in this direction, this spring will undergo certain amount of deflection. This will undergo another amount of deflection. So the total deflection of the mass will be delta 1 plus delta 2. Each spring undergoes different amount of displacements. So it is called a series connection. In series connection, 1 by K equivalent equals 1 by K1 plus 1 by K2, or K equivalent equals K1 K2 divided by K1 plus K2. In another case, there are suppose two springs are attached like this, parallel connection. In this case, when the mass undergoes a displacement, both the springs have to undergo the same displacement. Both of them undergo the same displacement. So in that case, the equivalent spring stiffness, if it is replaced by a single spring, the single spring stiffness K equivalent equal to K1 plus K2. So parallel connection, springs are equivalent spring constant is K1 plus K2. When the springs are in series, it is 1 by K1 plus 1 by K2 is equal to 1 by K equivalent. So these are the prerequisites for doing the numerical examples of this particular portion. Now we'll pass on to the numerical questions. If a helical spring having a stiffness 90 Newton per centimeter is available, what weight should be hung on it so that it will oscillate with a periodic time 1 second? So I've given the first step. The string's thickness is 90 Newton per centimeter. That is, in order to extend it through 1 centimeter, we have to apply a load of 90 Newton. So what will be the stiffness in Newton per meter? If it has to undergo 1 centimeter, we have to apply 90 Newton. So if it has to be extended by 1 meter, we have to apply 90 into 100. Okay, convert this centimeter. Now, 90 Newton per centimeter. So when the centimeter, so 90 Newton by centimeters in the denominator, how will you convert centimeter to meter? 1 by 100, isn't it? 1 centimeter, if you want to convert into meter, 1 by 100. So this is equal to 90 into 100 Newton per meter. So just understand the concept. 90 Newton is required for pulling it through 1 centimeter. So if you have to pull it through 1 meter, the stiffness is 9000 Newton per meter. That's the first step. If this is correct, the entire problem will be correct. If this goes wrong, the entire problem will go wrong. Period is equal to 1 second. If you are given period, we can find out the angular frequency from that, or vice versa. In some questions, you may be asked to find the period, we will be given the angular frequency. So period is 1 second means we have no omega into t is equal to 2 pi. Period is given, so omega is equal to 2 pi by t. So 2 pi radians per second. Now we have the equation for frequency. Omega is equal to root of k by m. So omega square will be k by m. Omega is now known. 2 pi square is equal to k, 9000 divided by 1. So we'll get 228 kilogram. So if you attach a mass 228 kilogram, it will have a period of oscillation 1 second. The question is, what is the weight to be hung? So the weight to be attached is equal to mass into acceleration due to gravity. So 2.237 kilonewton is the answer. Such questions are common for 3 marks in Part A. Next question. A weight 50 Newton suspended from a spring vibrates vertically with an amplitude 8 centimeter. Amplitude means maximum displacement from mean position. And frequency 1 oscillation per second. Find the stiffness of the spring, maximum tension induced in the spring, and maximum velocity of the weight. So let us see what are the data given. Weight is given 50 Newton. So we can get the mass. Amplitude, maximum displacement, that is R. We represent amplitude by the letter R. And frequency of vibration is 1 oscillation per second, or it is 1 hertz. So the frequency is given in hertz. From the frequency is given in hertz, we can convert it into radians per second. 1 cycle per second. 1 cycle is 2 pi radians. So 2 pi into f. 2 pi f will give you the frequency in radians per second. 50 Newton mass, it is converted into kilogram. Radius is, amplitude is represented by the letter R. 8 centimeters, we convert it into meter. Everything should be in SI system. The units are very, very important in dynamic analysis. Then stiffness of the spring, that's the first question. We have the only one expression we have studied so far. Omega is equal to root of k by m. So omega square is equal to k by m. Omega here 2 pi. 2 pi square is equal to k by m, 50 by 9.81. So from this we can get k, 201.22 Newton per meter. Second part, maximum tension in the spring. What will be the maximum tension in the spring? Spring force. Force in the spring will be spring constant K, or the stiffness of the spring into displacement. The maximum displacement is given not 8 meter. So the stiffness of the spring we have got in this step, stiffness into maximum displacement. 21.22 into maximum displacement give you the maximum tension in the spring. Maximum velocity, V is equal to R omega. Maximum velocity is equal to R omega. So omega we have got from here 2 pi, and R is equal to 0.08. So 0.502 meter per second is maximum velocity. just based on one equation, we can solve for any unknown data in this particular free vibration examples. Similar one, another one, frequency of free vibrations of a weight W with a spring constant K is 12 cycles per second. That is, initially when the weight was W and the stiffness was K, the frequency of vibration was 12 cycles per second. 12 cycles means 12 into 2 pi radians per second. So we got omega 2 pi f. Omega square is equal to k by m. Omega is equal to root of k by m, or omega square is equal to k by m. Just write 24 pi the whole square is equal to k, the stiffness. Masses, weight is W, W by 9.81, first equation. When an extra weight 20 Newton is coupled with the weight, frequency reduces to 10. So as the extra mass of 20 Newton is added, what is the weight of the system now? It is 10 cycles per second is the frequency. So 2 pi f, 2 pi 20 pi radians per second. The mass becomes 20 pi. That is equal to omega is equal to k by m. K by m. M is W is increased to W plus 20. So W plus 20, the whole divided by 9.81. So 24 pi square by 20 pi square. Equation 1 by 2 will get the value of W. Putting W in equation 1, so it's on page is reversed, I have to correct it. So this one, in this equation, in first case it was 24 pi, the second case it was 20 pi, isn't it? So 20 pi, the whole square is equal to K, the stiffness doesn't change, and weight changes to W plus 20. So instead of W, we plus W plus 20 divided by 9.81. So we solving 1 by 2, we have got the value of W. Once you get W, you substitute back in this equation and get the stiffness. So that is what is run here. So once you get W, you substitute in this equation 1 and we get the stiffness 26.338 kilonewton per meter. So coming to next question. Now question number 5. A body of mass 50 kilograms is suspended by two springs of stiffness 4 kilonewton per meter and 6 kilonewton per meter as shown figures A, B, C. This is figure A, this is figure B, and this is figure C. Calculate the frequency of oscillation. If the body is pulled 50 millimeter down from the equilibrium position and then released, calculate maximum velocity and maximum acceleration. We'll see one by one. Maximum velocity and maximum acceleration. Case 1, two springs of stiffness 6 and 4. These are arranged in series. So what will be the equivalent spring stiffness? 1 by K1 plus 1 by K2 is equal to 1 by K equivalent, or K equivalent equals K1 K2 by K1 plus K2. K1 K2 by K1 plus K2, we got the equivalent spring stiffness. Once we got the equivalent spring stiffness, omega is equal to root of K by M. Omega is equal to root of K by M. We'll get the frequency of vibration, angular frequency in radians per second. Then the natural frequency is usually expressed in hertz. 6.93 omega by 2 pi. We'll get the frequency in hertz. And V max, maximum velocity is R omega. That is why it is given. It is displaced from the mean position 50 millimeter. So 15 to 10 raised to minus 3 into omega. We'll get the maximum velocity. Maximum acceleration is omega squared R. So you got the maximum acceleration. The second case, this is the arrangement of the springs. One spring is 6 Newton per meter. Then the mass is attached. Then the spring. Then it is both ends are fixed. So what will happen here? When the amount by which this spring gets elongated will be the same as the amount by which this spring will get compressed. If the mass undergoes a displacement, suppose if this mass undergoes a displacement in vertical direction, this gets elongated, at the same time this gets compressed. So the displacements of both the springs are same. When the condition is, when each spring undergoes the same displacement, we call it as parallel connection. So this is similar to a parallel connection. It is not directly mentioned in the question, but we have to understand that this is a parallel connection. So K equivalent will be equal to K1 plus K2, 6 plus 4. 10 kilonewton per meter, converted into Newton per meter. This is very, very important unit. Omega is equal to root of K by M. So we'll get the answer as 14.14 radians per second. And the frequency is equal to omega per cycles per second expressed omega by 2 pi. We'll get 2.25 hertz. Here, the maximum velocity is r omega. This is omega. Amplitude is 15 to 10 raised to minus 3. You'll get the maximum velocity. Similarly, you'll get the maximum acceleration. And the third part of the question is, this is the third case. Here it is directly observed. Both the springs are in parallel connection. So this is also parallel connection. So whatever answer you have get for this case will be the same as this. Since they are in parallel, 6 plus 4, 10 will be the equivalent spring stiffness. So the answer is same as the previous one. Okay. Next question. A spring of stiffness 6 kilonewton per meter is cut into two halves and fixed to a mass m as shown in the figure. If the system vibrates with frequency 3 Hz, determine the mass m. So here a spring of stiffness 6 kilonewton per meter, that is cut into two. This is cut into two halves and it is attached to a mass like this. So this is also, we have just discussed, it's a parallel connection because the amount by which the first spring gets elongated is the same as the amount by which the second spring gets compressed. So both undergo the same displacement, so it is parallel connection. But a 6 kilonewton per meter spring, when it is cut, what will happen? The stiffness of each of these springs will be doubled. That is the point to be remembered here, because the stiffness of the spring is inversely proportional to the number of coils. So suppose if it was having 10 number of coils initially, when it's cut into two, each will become 5. So the number of coils decreases, the stiffness becomes inversely proportional to the number of coils. So it is equally cut into two halves. So when the spring is cut into two halves, stiffness of each half is doubled. So each of this spring is having a stiffness 2 times 6, so 12 kilonewton per meter. So this is 12 kilonewton per meter. This is also 12 kilonewton per meter. So this is parallel connection. So K equivalent is equal to K1 plus K2, 24 kilonewton per meter converted into Newton per meter. And you are given, its frequency of vibration is 3 cycles per second. So omega is equal to 2 pi f, you will get 6 pi radians per second. Omega square is equal to K by m, 6 pi square is equal to K by m. So the mass of the system is 67.55 kilogram. Thank you.